So my name is Brayden Nilson. I'm a Master Science NRS student at UNBC, and I'm also a physical scientist in the Western Air Quality Science Unit of Environment and Climate Change Canada. I want to thank everyone for inviting me to speak. And before we begin, I'd like to acknowledge that those of you that are joining from Prince George are meeting today on the unceded traditional territory of the Lheidli T'enneh First Nation. And I am presenting here in Vancouver from the unceded traditional territories of the Musqueam, Squamish, and Tsleil-Waututh nations. We thank them for allowing us to meet and learn on their territory. And I'll be presenting on recent work for myself, my master's supervisor, Dr. Peter Jackson, and my colleagues from Environment Climate Change Canada, Dr. Schiller and Dr. Parsons, looking at mapping, calibrating, and interpolating networks of fine particulate matter monitors in Canada with some specific examples from our recent work from Prince George. So first, I'll introduce fine particulate matter and its relevance for Canada and BC. And then I'll introduce a mapping tool that we have developed for visualizing this particulate matter data live. And the last half, I'll showcase some of our recent research using some of these low-cost monitors that measure fine particulate matter and show those examples local to Prince George. So fine particulate matter, or PM2.5, is a criteria air contaminant in Canada, meaning it's a primary focus for management and reduction. It consists of suspended particles less than 2.5 microns in diameter. And you can see on this nice graphic from the US EPA just how fine these particles are. They're about 1/20th the diameter of a human hair and quite a bit smaller than fine beach sand. These are suspended in the atmosphere where they can be respirated by people at the surface. So PM2.5 has many sources, most of which are summed up in this infographic from Health Canada. You can see burning candles and incense, fireplaces, wood stoves, gas stoves, some outdoor sources, including vehicle emissions, industry, wood burning. Something that's not included on here is wildfire smoke in general. But PM2.5 is primarily from combustion sources. And these particles can impact health because they can enter the lower respiratory tract if inhaled. And they can pass into the blood and cause a whole myriad of health concerns. Symptoms include irritation of mucous membranes, like your eyes, your nose, your ears, and your throat, decreased lung function, cough, and increased risk of lung and heart conditions. And there's even been some linkages made to higher risk for diabetes and Alzheimer's and other brain-related diseases. People who are at greatest risk are children, elderly, and people with pre-existing conditions of the heart and lung. And PM2.5 concentrations are highest globally in Asia and Africa. So the data shown here from this great report that's put out annually from Health Effects Institute and IHME called The State of the Global Air, which kind of summarizes the data available globally for key air pollutants, including PM2.5. The report that I'm citing here is from 2020, showing data from 2019. So here you see this map of the annual average, population-weighted average PM2.5 concentrations for each country. You can see that Canada is one of the top countries for the lowest PM2.5 when looking across a year and across the entire country. However, as everyone, at least in Prince George, is likely familiar, or those of you that live in BC, for part of each year, most of the province and the remainder of the Pacific coast and parts of Alberta and the territories to the north are impacted by wildfire smoke. So here we see daily snapshots of satellite images over BC and northern Washington from the MODIS Aqua satellite from October 1st to October 19th this year, showcasing some wildfire smoke impacts that really spread across the majority of the province this year. For reference, I pulled PM2.5 concentration data for this period for 3 cities across BC. So here in the south, we have Vancouver. Roughly in the middle, we have Prince George. And then up in the north, there's the Fort St. John station. So you can see a large amount of smoke blanketing the southern parts of BC near the end of this animation, but not nearly as much in the far north for Fort St. John. And really they're impacted by the Battleship Mountain fire that was burning to the west of them. And you can see these kind of episodic spikes in the PM2.5 record. And just for reference, the BC air quality objective for PM2.5 is 25 micrograms per cubic meter. So any observations higher than this value would be trigger an air quality advisory, which many of you being in Prince George are likely familiar with. So we see in Fort St. John spikes up to 150 micrograms per cubic meter, which is quite high, quite a bit higher than that standard of 25 that we raise alerts for. Prince George only got to about 60 to 70 micrograms per cubic meter, kind of peaking near the end of this animation. And then Vancouver saw upwards of 100 micrograms as well. Again, right at the end of this animation where you see that smoke filling all the valleys and spreading across. I'll just let that animation wrap up before I go on. So, however, just because we see smoke from satellites doesn't mean it's actually reaching the surface where people are breathing it. Here we see two snapshots from the same satellite of this previous animation. The first on the left is from October 6th. This is a day with a lot of visible smoke over Vancouver. But if we look at the concentrations pulled from those same monitors I was just talking about, I just put them above the image there. The concentrations in Vancouver were not abnormally high. We had 20 micrograms per cubic meter was the max recorded this day. Whereas, like I said on the previous slide, 25 is kind of that standard for above that, we raise these air quality alerts. Meanwhile, in Fort St. John, up in the north, they had values of 85 on average for that day. And you can see some of that smoke from the Battleship Mountain fire spreading across the city here. So given that the concentrations are low in Vancouver, we can make the assumption that smoke is probably not reaching the surface down here, even though we can see it from the satellites. It's likely higher up in the atmosphere. And I went and found a tweet from somebody at the same time that night on October 6th, where they're pointing out this big bright sunset that they could see. I just want you to notice that at the surface in this photo, it's quite clear. You can see across the other side of the water. It doesn't really look like there's any smoke at the surface. But with this big red sunset, it tells us that there is smoke in the upper parts of the atmosphere, reflecting those light rays back down and giving this very pretty sunset. On the right, there's a snapshot from the end of the animation that was shown in the last slide. This time showing a lot of smoke filling the valleys to the south. You can even start to pick out some of those valleys with the smoke that's filling them. And if we look at a news article from Vancouver for the same day, you can really see the difference with all that smoke sitting at the surface. People are breathing this in, and concentrations were above 100 micrograms per cubic meter this day in Vancouver. So surface concentrations of PM2.5 typically come from regulatory FEM, or federal equivalent method, or FEM. I'll be referring to them a lot as FEM through this talk, FEM monitors. So here's a map of BC with the locations of these FEM monitors shown, typically one or a few in major cities. We have one in Prince George. And then as you get into the lower Fraser Valley and on the islands where there's higher densities of populations, they tend to have a few more monitors. So PM2.5 is measured as the mass concentration of particles averaged over the past hour, typically in units of micrograms of particles per meter cubed of air. Values less than 15 micrograms per cubic meter are typical for BC and Canada. You can have episodic periods, especially in the winters in the interior, where atmospheric conversions lead to the buildup of pollution, and you can see values, somewhere between 20 to 60 to 80 micrograms per cubic meter. And then if we have wildfire smoke impacts, like you saw on the previous slides, values can reach above 100 micrograms per cubic meter. And I've even seen above 300 in some of the worst wildfire years. Just to bring this a little close to home, here's the Plaza 400 site in Prince George. This is at the Ministry of Environment building. The Ramada is kind of kitty corner to this. We're standing on the intersection of 4th Ave and Queensway. And you can just see the inlets of the monitors up at the top of this roof here, and as well as some other weather measuring equipment. So alongside these FEM monitors, which is roughly 45 total in BC, there's about 350 low-cost PM2.5 monitors that have been installed across the province, as well as the rest of Canada. I believe there's about 800 that are actively monitoring PM2.5 in Canada right now. So on the screen here, there's a map with larger circles that it might be a little bit hard to see. Hopefully it's clear, but the large circles indicate the locations of the FEM monitors. So this is the regulatory network. And then those tiny circles are various low-cost monitors that are installed by different agencies or the public themselves, which really helps to increase the amount of communities that can be informed about their local PM2.5 concentrations, which is very important during wildfire smoke season, where that smoke could be almost anywhere. So here on the left is an example of a regulatory FEM PM2.5 monitor. This is a MET1 BAM 1020, which is fairly commonly used, especially in the US. Here we have the instrument on the bottom. This is where the actual sensing of and counting of the number of particles and the density of particles is done. Above, you have a tube that's typically insulated, or a pipe that runs. It can just be on top of the monitor like you're seeing here, or it can run quite longer up through a roof like you see in this diagram. The Prince George Plaza 400 site has those inlets that we saw way on the top of the roof. The pipe runs down, and then the instrument sits in a weatherproofed enclosure where it's safe from rain and wind. On the right, and then at the top of the pipe is a cyclone inlet, which essentially separates out the smaller particles so that we're only getting particles less than 2.5 microns in diameter passing to the instrument for sensing. On the right here is a purple air monitor. This is a very common low-cost monitor that's used across Canada. And you can see how they're quite a bit smaller. They're about the same size as this water trap here on the FEM. You can see them installed in a public area in the image in the top right. And these monitors are small, they're inexpensive, and they're relatively set and forget compared to the FEM monitors. So they require very little maintenance. You can mostly just set them up, connect them to a Wi-Fi, and then reset the Wi-Fi if someone's password is changed, or change out a sensor if it starts reading a little wonky. So there was my just a bit of an intro before getting into more of the talk. So just a little recap of what we covered so far. I talked about fine particulate matter, or PM2.5, how it's a subset of airborne particles with those diameters less than 2.5 microns. Concentrations of PM2.5 are relatively low for most of the year. However, it makes up a major component of smoke. And as many of you know, we are regularly impacted by wildfire smoke in the summer and fall seasons in BC. PM2.5 is monitored in real time by regulatory FEM monitors. These are quite large, they're expensive, and they require regular maintenance. But they provide the highest accuracy gold standard data we have available for real-time observations of PM2.5. There are also low-cost monitors, which I'll be talking about a lot through this presentation, specifically those from Purple Air. These are small, they're inexpensive, and they're rarely maintained, which allows you to install them in much larger numbers. However, they do have that lower accuracy, that not quite the gold standard that the FEM monitors reach. So this brings us to our web mapping tool, AQMap. You can access this through any browser at cyclone.umbc.ca/AQMap, and the link is just available on the slide there. And we developed this in order to display PM2.5 observations from FEM and low-cost monitors, such as the Purple Air that I've been talking about, as well as another from a company called AQA, which uses the same sensors internally. There's also several smoke-related layers in the top right menu up here. You can see active fire locations, fire danger ratings, and various model outputs that help add some extra context to the observations, especially during wildfire smoke season. The low-cost monitor data are corrected by default, and I'll get into this correction more in the next section of this talk. But essentially, it helps bring the data from the low-cost monitors more in line with those from the FEM, so we can have a better trust in the values that we're receiving from them. This map is updated every 10 minutes as the Purple Air data become available, and every hour as the FEM data are released. We have a French version available here for those who are interested. It's the same version as the website, it's just the languages, the English is translated to French. And for any other extra information about the website, low-cost sensors, the correction, and general information about air quality, you can click on here, or you can reach out to me as well. I'm always open to an email. But AQMap is really great, allowing anyone to visualize their local air quality in Canada, especially areas which might be impacted by high PM2.5. So here we see a recent snapshot of the monitors local to Prince George. I think I took this November 3rd in the afternoon. There's one FEM located downtown at the Plaza 400 building, which I showed that photo of earlier. So a nice thing with this AQMap is that you can click on any of these monitors and you can see a nice summary of the data and a record for the past 2 weeks up to a year and a half of the observations recorded. So here we see a nice little time series from the FEM site showing some relatively higher concentrations kind of around November 1st at midnight. There's roughly 40 Purple Air monitors installed around the city at this time. I think there's been close to 50 at other times. It just depends on the availability of monitors, if they're connected to the Wi-Fi correctly or not, if they're being maintained, if they're going through maintenance. So you can pull the data from those as well. Here's a time series of one of the Purple Air monitors located in the northeast corner of the map, of Prince George, sorry, relatively close to the high industry, heavy industry areas. And if you want to compare the purple layers directly with the FEMs, you can do that as well. So here we're looking at a comparison between this purple layer that's about 1 kilometer away from the Plaza 400 site. You have the FEM data on the y-axis and the purple layer data on the x. And then there's a one-to-one line running through. And so the goal here being that you want all those points to be as close to that one-to-one line as possible. And here we see that it performs fairly well. So you can kind of have a better trust for the purple layer data, at least in this area. AQMap is also very useful for seeing where smoke is at the surface. So if we take if we look at this animation through screenshots of the map taken during the most recent wildfire smoke event, so this is the end of that animation, October 18th. So this is showing for the hours from 5 in the morning to about 4 in the afternoon. And you can really see that smoke building up in the south, those colors going from light blue to yellow to orange to dark red. And that's really where as the smoke is settling down in the areas. If we pull the observation data from the Tsawwassen station, which is at the ferry terminal in Vancouver, you can see some major smoke impacts beginning around 11 to noonish at this area, with concentrations of PM2.5 rising to over 100 micrograms per cubic meter. Meanwhile, if we look at a station in Golden, BC, which is a bit separated away from where the smoke was present, you can see little to no smoke impacts, and the concentrations stay between about 5 to 15 micrograms per cubic meter, which is fairly typical for BC sites. So alongside this observation data, you can use model outputs and analysis products to get a more complete picture of where the smoke may be on the surface. I have two screenshots here, again, from that October 18th event. On the left is a smoke dispersion model output that's available on our map. And you can see that it lines up fairly well with the observation stations. This is essentially where a model thinks smoke from wildfires is sitting on the surface. And you can see this kind of arc of sensors are green here, right on the edge of Vancouver and between the island. On the right, we see hand-drawn smoke density polygons from the hazard mapping system produced in the US. This is essentially where an expert thinks smoke is present that day. They do that in the morning and they update the polygons throughout the day. And this is regardless of whether the smoke is at the surface or not. So similar to when we were looking at the animation and you could see smoke over top of Vancouver, but it's not necessarily impacting the city and the people within it. Animation messed up a little bit here, but let's just pretend you can't see those text boxes. So AQMap is a collaborative product between UNBC and Environment and Climate Change Canada. It started in 2018. It was just a UNBC project. Dr. Jackson and myself created this mapping tool just specifically over BC. In 2019, we joined forces with Environment and Climate Change Canada, and AQMap has expanded to the Western provinces and territories. In 2020, the map was revamped to be more efficient and it was expanded to all of Canada, continuing this collaboration with Environment and Climate Change Canada. 2021, we created a French version, given that Canada is a bilingual country. And even now, we're continuing development on the map. As bugs and issues appear, we're fixing them and adding new features. And Environment Canada has a ongoing pilot project. It's been going on for a few years now, and it's continuing on into the future, where we're sending these low-cost monitors out to regions that don't have PM2.5 observations. We're sending batches of 10 to 20 typically to, say, up into the territories. And then those agencies are going and installing them within their cities and areas that do not have these observation data. I think there's already, a third roughly of all the purple layers in Canada has been a result of this pilot project. And so that's, I think, about 300 of the 900 or so. So just a quick recap before we get into the research that we've recently been doing with these sensors. We talked about what fine particulate matter PM2.5 is and how it's monitored in real time using originally FEM monitors, but more recently low-cost monitors have become more popular. And then I just wrapped up talking about our mapping tool AQMap, which is a platform for displaying this real-time PM2.5 data. There's a link on the slide there for if you missed it from before and you're interested. And this map is useful for locating smoke impacts, as well as just being, if you're interested in air quality in general, you're able to see your local air quality. And it's a collaboration between UNBC and Environment Canada, which we're continuing to work on. And monitors are being installed by both the public and Environment Canada across the country. So as we started to work with this data, us and many others noticed that purple air monitors tend to read higher than FEM monitors, especially at higher humidity levels. So if we look at this plot on the left here, it's just a simple scatter with the reference observations from FEM monitors on the y-axis, and then observations from co-located purple airs along the x-axis. So these are monitors, purple air monitors that are installed at the same location as an FEM. And we're looking at data from sites across Canada and the US. I believe there's 47 sites that are being summarized here. So there's a couple lines drawn on this plot. The top one, this one right here, is essentially the 2-to-1 line. So if you're to the left of this, then your purple air observations are about half or less than that of the FEM. So if the FEM is reading 1,000 for that hour, the purple air is reporting 500, which is not necessarily something we want. The next line is the 1-to-1 line. So this is where we want all the data to be lining up on. It's where purple air is equal to FEM. And then the last line is the 1-to-2 line. So it's where the purple airs are 2 times that of the FEM data. If we look at the, oh, and then I should say that the colors on this plot indicate the number of observation points within that region of the plot, the little hexagons there. And it's a logarithmic scale. So wherever you see a brighter color is a significantly higher density of observations in that area. So if we were to just draw a quick line through this, you'd see that it's trending more towards that double of FEM, but there is variation around that line. Now, if we look at the plot on the right, we can see that this impact is exacerbated as humidity levels increase. So on the y-axis, we have groupings of dry, moderate, and humid relative humidities. And then on the x, it's the medium PM2.5 concentrations for various sites, the same sites that are summarized in the plot to the left. And so the purple air data are in the purple box plots, and the FEM data are in the gray. And you can really start to see how those boxes spread apart and the bias between the purple airs and the FEMs increase as humidity increases. So we have a recent publication that explores this issue, and we present a general use correction formula that can be used to bring these data more in line with the FEM observations. So there's a snapshot of the publication there. It was published in Atmospheric Measurement Techniques earlier this year. The DOI is in the top left corner. It's all publicly available, open source, so you don't need to be registered to a journal or subscribed to a journal to be able to access it. And if you would like a copy of it and you don't get it during this presentation, just reach out to me. I'll have my email at the last slide. And I'll be happy to send you a copy. So for this work, we had to select a number of sites in order to where purple airs were co-located with FEM monitors in order to build and train and test the models that we have built. So we selected 47 sites across Canada and the US. 32 of those we used for training sites, and these were used to create correction models in order to test. And the remaining 15 sites were used to evaluate the performance of those models. We selected these sites using 3 main criteria. First, we looked for FEM locations that had hourly PM2.5 concentrations and at least 1 purple air within 50 meters. Second, the monitors had to at least have half a year of valid QA/QC overlapping data between the purple air and the FEM. And the hourly PM2.5 correlation between the 2 monitors needed to be at least 50%. And this was just to ensure that the purple airs were actually located where we thought they were and not misregistered on the map and actually located in a different province or state entirely. So in this work, we developed 4 models, which are at the top of this table here. And we actually developed many more than this, but these are the 4 that made it into the paper as the best performing. And we had compared these with 4 published models that can be found in the literature and are used on other mapping platforms like Purple Air's proprietary map. I'm not going to get into the models in detail here. You can go into our paper if you want to dig into them some more. But the important thing I want to note here is the different variations in forms that we were testing. We looked at various simple linear models, multiple linear regressions with relative humidity and temperature. There's a polynomial in there and a piecewise. But so there was a varied, the relationship was complex between the purple air data and relative humidity. And so we were able to tease it out, hopefully, with these models. So when evaluating the performance of the models, we wanted to look across a range of concentrations. We didn't want to just give a single evaluation to say that this model works best. We wanted to say if it works better in the low range, in the moderate range, or in the high range. So that's what this plot attempts to do here. On the x-axis, we have the range of concentrations, and it's shown using the Canadian AQHI Plus system, which is the Air Quality Health Index Plus. And that's summarized here on the left, where essentially you break down the concentration ranges into 10 microgram per cubic meter bins. So from 0 to 10 is a value of 1, from 11 to 20 is a value of 2, and so on until you get above 101 micrograms per cubic meter, which is assigned a value of 10 plus. So you see that along the x-axis, essentially evaluating the range of concentrations for each model. And the y-axis is the individual models as well as the raw data situation at the top. The values in the color that are being displayed on the plot is essentially the bias between the purple airs and the FEMs for this AQHI plus value. So if you had a value of -2, it means on average over the period of record that the purple airs were recording 2 AQHI plus units lower than the FEM, which is something that we do not want. You want to be roughly within that same unit. So here we're looking to get as much gray or as much close to 0 bias as we can. And we selected models 1, 2, 5, and 7 for this reason. You can see model 2 as being marginally the better performer than the other 3, with model 1 being the worst of the 4. So we took those 4 models that we found best from that previous slide, and we drilled down on them a little bit more. Here, it's a similar plot with the FEM AQHI plus on the X. So you're seeing that range of concentrations being evaluated. And then each panel is a different performance statistic. The 2 on the top are commonly used error statistics, and the 2 on the bottom are commonly used bias statistics. There's 2 lines, or well, 3 lines, I guess, in each of these plots. There's the dashed line and the dotted lines. These are acceptable levels and goal levels that are defined in a previous study by Boland and Russell in 2006, Boland and Russell. And then there's also a solid black line that indicates the best, and that's at 0. For all of these panels, you want to have as low error or as low bias as possible, as close to 0. So here we see that models 2 and model 7, 2 being the red line with the circles, and model 7 being the blue line with the diamonds, gave the best performance over the range of concentrations, especially after the low range, higher than 3 AQHI plus. So here is our model 2 that we selected for our general use, or at least the form of our model 2. This form was derived from, it was taken from Crowley et al. 2018. And they have this hygroscopic growth factor K that we fit a value of 0.24 based on our 32 training sites. We also found that the correction model works better when we bounded the relative humidity to 30% to 70%. And this is just due to how the properties of the particles change outside of these bounds. And the correction model tended to be overcorrecting when outside of 30 to 70%. So that wraps up that recent paper on our low-cost sensor corrections. So just a little quick recap before I get into the last section of this talk. So we talked about fine particulate matter and PM2.5, how it's monitored, what it is. We talked about our AQMap tool for displaying the data from various monitors in Canada. And then I just wrapped up that talk about the low-cost sensor corrections and how they're useful for bringing the data as in line with FEM monitors as possible. They're created and evaluated using data from co-located monitors where purple air is right beside an FEM, reading the same air. They should account for impacts of humidity, as we found that to be quite significant, and they should be evaluated across a range of concentrations so you can see how well the model is performing in different situations. So we have a second paper that's currently in development that looks at the low-cost monitor data that we have for Prince George for the year of 2020. So there's just a little screenshot of the paper here. It's not in the publishing stage yet, but we're getting close to that. And essentially what we did for the study was we collected the data for PM2.5 monitors in Prince George for the year of 2020. We modified and tested a wind-based interpolation method to take these point observations and then turn them into a gridded data set over the city. We then summarized these grids to produce seasonal and annual summaries of PM2.5 across Prince George, which we then compared with annual and 24-hour BC air quality objectives to see how well Prince George met these levels. So we selected the year 2020 because it was when there was the peak number of active purple air monitors in Prince George. Excuse me. We had 47 monitors at the time, as well as 5 or 6 extra that are outside of the map view that you can see here. We chose this kind of zoomed in view of print storage as it covered most of the residential areas and didn't leave us with too large of a grid for our interpolation method, purely for resources and time's sake. So we see a table on the left here with all the individual purple layers that were used in the study. But the one thing I want to highlight here is that since we were using a 1 kilometer by 1 kilometer resolution grid for our interpolation over the city, that there were some locations that had more than 1 purple layer within them. So specifically this location here at the Plaza 400 site, there was 3 purple layer monitors located there. And then in this top right corner, there was 2 within the same grid cell. So we averaged those together into 1 before the interpolation, just to make it more comparable with the other locations. So you can see a pretty good coverage of monitors across the city. I believe it was about 11% of the grid cells shown here have an observation station within them. So then we need to go through the process of interpolating these observation points and really fill in this grid and all those empty holes. Before we got into that, though, we wanted to make sure that the purple layer data that we had in print storage was comparable with the FEM observations, so we could have some strength to this method. So it's worth so what we're seeing on this plot here is the daily mean PM2.5 concentration for each of the months for this year of 2020. And we're going from December to November because that is more considered the meteorological year, since winter tends to start more in December than it does in January. So we have this kind of shifted back a month, but I'll still refer to it as the year of 2020. There was no FEM data available for December or August and part of September, but we have purple layer data available for the entire period. And I should say that this is these are the purple layers that are at the Plaza 400 site, co-located right near the inlet for that FEM monitor. There was a period in September where the FEM data was unusually high for a few weeks. It was immediately following after a large gap in August and the beginning of September where there was no data. And there was another smaller gap right after this offset where the FEM data began reading in line with the purple layers afterwards. So it's unclear to us if this is just an issue with the FEM monitor or if the purple layers themselves missed something that the FEM was picking up. But otherwise, for each of the other months, the purple layers were in quite well agreement with the FEM data. You can see those boxes sitting quite close to each other for the daily averages. And it ranged from about 1 to 2 micrograms per cubic meter that the purple layers were lower than the FEMs on average during this period. So we were pretty happy with the performance. And I should also say that this is having our correction model applied because we were seeing before that purple layers were reading higher than FEMs, but after applying the correction model, it overcorrected slightly and lowered them down, but still brings them pretty close to in line with the FEM observations. So then in order to interpolate these point observations into a grid, we improved upon a published interpolation method, which relies on the shortest wind path distance. So this is very similar to an inverse distance interpolation method. However, instead of using the Euclidean distance between each point, the physical, like how many kilometers between this point and the next point, instead it uses the shortest wind path. So it takes into consideration the wind directions along the way and adds to that distance if the wind is resisting the motion. So this paper from Lee et al. 2014, which this interpolation method was originally published in, has this useful summary image that I'll just kind of step you guys through, just to give an overview of how this interpolation method is performed. So first you have gridded wind directions. So for print storage, we have a research model that has 1 kilometer by 1 kilometer resolution wind data that we use for our interpolation. Then for a grid cell, you calculate the cost based on the wind direction for each of its neighbors. And I'll show the cost calculation in a second here. And you do this for every single cell. So you end up with this matrix that you can see in the background where the motion between each point has a cost value associated with it. And with all these cost values, you sum it up and you find the path with the lowest cost. And you use that as the distance between your 2 points you're trying to interpolate. So here's that cost calculation at the top. There's a decent amount of text there explaining it, but it's relatively straightforward. You have this F function, which calculates an azimuth, so an angle from 0 to 180 between the motion of the path of motion between the 2 cells that you're trying to calculate the cost for, and the direction of the winds at both of those cells. And then you multiply it by 1 if the cells are beside each other, or by the square root of 2 if they're diagonal, which helps to bring in that kind of Euclidean factor for the physical distance between points. For our work, we modified this cost calculation. So now that the F function calculates the inlineness, which instead of being a degree from 0 to 180, which it matters if you're upwind or downwind, now it returns a value between 0 and 90 of the wind direction of path of motion. So it doesn't matter if you're upwind or downwind. All that matters is if you're parallel or perpendicular to the wind and how much. We also added the second factor here that looks at the wind speeds and helps adjust the cost, essentially increasing the distance if you have a lower wind speed. So really all we changed was this step 2, the cost calculation. We felt we improved upon it, and I'll explain why here shortly. But really, these costs, they just get summed up and used as the distance for a regular inverse distance weighted method. So it's not overly complex. We're just, instead of using a normal distance between 2 points, we're getting this wind path distance using this cost calculation. So for those of you who are familiar with inverse distance interpolation methods, you tend to get these circular shapes around your observation points. So say if we had this X was an observation monitor, you'd end up having a circle around it because it doesn't consider wind. It's only thinking of the distance between the grid cells and the observation it's trying to interpolate with. The original wind-based method, which I discussed on the left, has more of a teardrop shape that points downwind. So you can think of this more akin to if you had an industrial stack emitting PM2.5 and the wind blowing it down and how it would spread. So we felt there was an issue with this because these are observation stations, not emission sources. So really the pollution should be blowing past the monitor, so it should be above and it should be upwind and downwind from the monitor location. So in our modified method, we get this more eye or lens shape, like I said, where it's above or it's behind and ahead of the wind. And as the wind speed increases, that gets more exaggerated. And if the wind speed decreases, it gets closer to a circular shape, which we feel is more representative of how air pollution is moved with the wind. So in order to evaluate that this adjusted interpolation method was actually successful and actually was useful to use, we left out 7 observation stations from our grid. We ran the interpolations, and then we compared the interpolated data at those locations with the left out observations. So here you can see a summary of those statistics. So we have each of the banded rows is a different season. Within those, we did this for a regular inverse distance method, so just using the Euclidean distance, not including wind. We did this for our wind-based method, and then we found the difference between the two. And we calculated mean bias, normalized mean bias, mean error, normalized mean error, and root mean square error for each of these scenarios. So you don't need to look at this too much. The main thing I want to highlight here is that we saw a 2 to 7% improvement when using our wind-based method across all seasons. It was, I think, just in summer for the normalized mean error was it comparable, but in all other cases, we saw this improvement upon using our wind-based method. So then we interpolated all the hours for the meteorological year of 2020, so from December 2019 to November 2020. And you can see a snapshot of the first week of those here. I'm not going to play the full year because it would take too long to go through all the hours within a single year. But we took these grids and we averaged them into seasonal summaries, which you can see in this image to the right. So just for some contextual awareness, for those of you who don't know Prince George or who can't see the map very well in the background, you have the downtown bowl area here. You have the Fraser River running from the northeast to the south and the heavy industry region to the northeast, the BCR industrial region to the south. We have the Hart region up here, the Nechaka running in from the northwest, and the College Heights region down to the southwest. So we felt that these interpolated grids actually fit fairly well what we would have expected to see for Prince George. You have a higher concentration in the winter versus any of the other seasons. This is where we have lower temperatures and we tend to get thermal inversions, which lead to the buildup of pollution within the river valley bottoms. You have a higher concentration at the confluence between the southern industrial area and the industrial area to the northeast. And you also have some higher concentrations observed around this industrial area to the northeast as well. As we move into spring and summer, the winds pick up, the pollution gets moved out a little bit easier, and we don't see these same high values that we're seeing in the winter. And then in the fall, it starts trending back towards that higher concentration state. Here's just a temporal look at the grids that we produced. So this is essentially, it's a little bit complex, but essentially for every hour, we averaged the grids for the past 24 hours to produce 24-hour average grids for every hour. So then we displayed on here the minimum value for each of those grids for that hour, the mean of all the values in that grid, and the maximum value. So you can see essentially when what most of the locations in Prince George from our interpolation were reading for that hour, and what at least one location was from the max. Also on this plot is drawn the BC 24-hour PM2.5 objective of 25 micrograms per cubic meter. So this is the one that when concentrations go above this, an air quality advisory is raised for the city. So if we block out everything below that line, you can see that there was quite a few events in the winter of this year. This is when we have those thermal inversions and PM2.5 is building up in the city, not able to escape from the river valleys. There's one tiny little spot in the spring here where we just go slightly above it. There's none in the summer. And then we have these events in the fall here, which were likely linked to wildfire smoke. For those who were in Prince George in 2020, you may remember that this was a fairly relaxed year for wildfires around in the interior. And really, we just got smoke coming up from northern Washington and southern parts of BC and just catching the edge of it in Prince George. So we only had a few days there where PM2.5 levels were above the objective. So here on the left, we have a similar grid to those seasonal ones I was showing before, but now this is averaged over the entire year. And we use this to evaluate where Prince George did or did not meet the annual objective from BC of 8 micrograms per cubic meter. So we see here that all values are below 8. The scale only goes to 8 at that yellow color. So all locations in Prince George for the year 2020 met the annual objective of 8 micrograms per cubic meter. However, there is an aspirational goal of 6 micrograms per cubic meter. And these regions outlined in red were above that for this period. On the right, we see the percent of hours where a specific location exceeded the 24-hour objective. So the same idea as that time series I was showing before, but now spread a spatial representation of it. And so you can see the downtown core, the eastern side of it, having between 1% and 2% of the hours exceeding in an entire year exceeding that 24-hour objective. So that about wraps up what I want to talk to you all about. Just a quick summary of what we went through. We talked about PM2.5 and its impacts. I showed these satellite images of smoke spreading across BC from this year. We talked about the usefulness of our web mapping tool, AQMap. There's a link there for those who missed it. We talked about our recent publication on the importance of correcting low-cost sensor data. And I just wrapped up speaking about the local impacts of PM2.5 in Prince George from some of our more recent in-progress work. So with that, I'd like to pass it off to you guys for if you have any questions. And if there's anything that you can't get to, that you aren't able to ask now, or if you think of later, if you want to really just chat about anything to do with any of this, my email's up in the top right there. Feel free to reach out to me. I'd be happy to take any questions. Thanks, everyone.
Thanks very much, Brayden. And for those folks who are online, you can either put your question in the Q&A box or the chat session, and I'll read them out. And so we do have a question from Jouet Dong. Is this wind interpolation method applicable to large areas, say the whole BC province?
Yeah, we haven't explored that yet, but we believe it would be. Some future work will be looking into it. The main issue is that most larger scale wind models that are available right now have about a resolution of 2.5 kilometers up to 10 kilometers. And while the ones we're using for Prince George was a 1 kilometer resolution. So there could be some issues with not having fine enough resolution data in order to spread it, say, over BC or look over Canada, but it's something that we're going to explore in the future.
Thanks, Brayden. Any other questions online or in the room here, folks?
Ask.
Go ahead, Chibuki.
Okay, so your presentation was so nice. I mean, the use of wind speed to, especially for the local air quality in Prince George here was, it was novel. When how you kind of include the winds, because when I compared the method you cited and the one you use is kind of you included the wind speed parameter. But I'm just wondering for for the work you did for 2020, I think is this is a year that's impacted by COVID, as we had a lot of lockdowns. So I'm wondering if when you compare the that factor to the maps you produce, if this is something that will be really important to the policy we have for PM 2.5 control in Prince George. I mean, considering the year you used.
Yeah, no, actually, I hadn't thought about that. There would be some significant impacts, like we saw. Pollution around airports was reduced significantly during the COVID lockdowns because people weren't flying nearly as often or at all. Yeah, I would expect to see some different trends in Prince George. At least this is averaged over an entire year. So you have a bit more strength from that. But yeah, I would expect to see quite a bit different reports depending on the year that you selected.
Of course, there have been quite a few papers looking at the impact of the lockdowns on different air pollution levels, especially in large urban areas with NO2 and other kinds of pollutants. I wonder though, in Prince George, folks huddled around their homes, maybe burning more wood in their fireplaces. The pollution levels might actually have gone up. It's hard to say for sure. They're quite high in the winter, obviously.
And that could be why we have such higher concentrations in the winter this year compared to the other as well. Maybe, like Peter said, they're burning more wood because they're indoors more often. People are working from home, not going to the office.
Can I ask some more?
Yeah.
There's one more online. Okay, sorry. Maybe the person online you could read it up. Read the person for the person online.
Okay, so Brian McEwen has asked me a question. This is interesting prospects in terms of establishing background air quality concentrations that are used for regulatory modeling. Has there been much discussion to this effect with regulators?
So we're really just starting to get into the integrating the low-cost monitor data into, say, Environment Canada's products. At the moment, there are people looking at the data, and it is being considered for impacting regulations. But right now, at least, it's not being used directly. The provinces are still relying on the FEM data for the most part.
I think Brian was referring specifically to the idea of background concentrations, because background is a tricky thing to assess. Do you have any comments regarding the use of these monitors for assessing background levels specifically?
Yeah, they're definitely useful. The main issue that I could see with it is, especially when you're trying to get background areas, you're using the monitors that are much farther away from the city, not being impacted by the city's emissions. So if you don't have multiple monitors in that location and one monitor starts to read a little bit weird, it could impact your background concentrations that you use. So it's definitely possible and definitely doable, but you would want to be cautious with using the data if you can't necessarily correlate it with an FEM monitor that's within a reasonable distance.
Go ahead, okay.
So for the work you did with the bias correction of the data collected from popular monitors, I saw you used like much of it was dependent on relative humidity, which is also good, I mean, it's one of the factors. But I was wondering if you had time to look into the effect of temperature. Like I know for certain that the time we had a previous monitoring equipment before the introduction of the BAM sharp, one of the problems was I think the previous equipment used to read lower values in winter. So I don't know if you kind of had time to look into the effect of temperature on the.
We did explore it a bit. Oh, sorry, Chibuki. We did explore it a bit. In the work before that got published, when we were playing around with a bunch of different models, we were, including temperature, not including temperature, including humidity, not including the combination of the two. And we found that I think it's probably the relationship between temperature and relative humidity was too dependent on each other. So as long as you included one, you didn't it didn't change the results too much if you included both
Okay.
or the other. But yeah, we would expect to see, you can get ice crystals being picked up in the monitors. You can get buildup of ice that's preventing particles from coming in. So there is a temperature effect. It was just a little too hard to tease out in the data that we had available.
Great. Are there any more questions either from the online group or from the people in the room here? We're actually nearing the end of our appointed time anyway. This presentation is being recorded and will be available. I'm not sure where exactly yet, but if you're interested in viewing the recording, send me an email and I'll let you know where we wind up posting it. Once again, I'd like to thank you very much, Brayden, for stepping up and making the first in 4.5 years of our Science Informal Seminars. Thank you very much, Brayden.
No, I appreciate it for letting me speak here. Thank you.
Thanks to those of you who attended online as well. We had 18 attendees online, which was awesome. Thank you very much. So I'll close the session now.
Thanks, everyone.
Thanks,
Bye,
Brayden.
Brayden.